All right, so hi everyone, I'm David, and welcome to the Data Council London Meetup. Um, for those of you who have attended our past events, nice to see you again. And for those of you who are new, welcome. Here's the agenda for today. So we're going to start with some quick introductions on housekeeping and Data Council, followed by the first talk, which will be delivered by Upkar. He'll tell us more about some techniques to remove unfair bias in machine learning. And the second talk will be by Watt, who will share with us some of the data challenges and the different analytics roles at Facebook. Some housekeeping notes. Today's online event is recorded and it will be published onto YouTube. The link will be shared with you guys within the next few days. As for the Q&A for the talks, I've checked with Upkar and Watt. They are happy for you guys to jump in anytime during the talk. If you have any questions, there will also be Q&A at the end of the talk. And feel free to type any questions in the chat box as well. Quick introduction on Data Council for those who are new. Data Council fundamentally is a community-powered group that aims to build data communities across the world. And we do so by organizing high-quality events like conferences and meetups across the world. In the past few years, we have been holding conferences every year in San Francisco, in New York, Barcelona, and Singapore. And on top of that, we have also regular meetups across many major cities. And these meetups are all run by volunteers like me and Adam Heinzinger, who unfortunately can't join us today. We're both engineers. We're not doing this. We're not paid to do this, but we're doing this because we really enjoy meeting people at these meetups, and also we're keen to build the data community in London. So if any of you is keen to help organize a future event, or to give a talk, or to sponsor any future events, please do reach out to me at the end of the session. So that's Data Council in a nutshell. Today's event is very kindly sponsored by IBM. A special thanks to IBM for enabling us to continue to run our events for the community. We have Tim with us today. He's from IBM. Tim, would you like to say a few words?
Yeah, sure. Can you guys hear me okay?
Yeah.
Awesome. Yeah, so my name is Tim Bonneman. I work on the IBM data science community team. We're a small group normally based out of San Francisco, currently all working from home. We are providing a space for over tens of thousands data scientists, machine learning, and AI engineers, really a place for data scientists, by data scientists, with lots of learning resources and access to some of our most esteemed experts. So definitely check it out, give it a look. Right now, if you join the community, you get access to a complimentary 1 month of select IBM data science and AI courses on Coursera to sweeten the deal. And yeah, give it a look. Very happy to sponsor another meetup here with Data Council, and I hand it back over to David.
Thanks, Tim. So as mentioned by Tim, there are tons of great resources by IBM online, and especially in this Coursera course as well. So do check it out. As mentioned, this video will be posted on YouTube, so you can refer back to this link later on as well. All right, I think we're ready for our first talk. So the first talk is on removing unfair bias in machine learning by Upkar, sorry. And he's the IBM data science and AI developer advocate. Upkar, over to you.
Okay, thank you. Can you please enable screen sharing for me, then I can start.
Yeah, let me do that. Give me a second. All right, can you try that again?
How does that look?
Yeah, that works.
All right, so you can see my slides?
Yes.
Perfect. Hi, everyone. Thank you for the warm welcome, David. Again, my name is Upkar. I work for IBM. I'm a developer advocate here. And today we'll talk about AI fairness. What does that mean? And then more importantly, how to detect bias in your data set, in your models, and then how to go about mitigating it. I'll show you some algorithms that we have in a very open source toolkit that hopefully you'll find useful. So I'm actually curious in the chat, can folks put in if you've worked with fairness in the past? What is your experience like? If you've used any tools, I'm very curious to see if you have. And we'll keep this fairly interactive here. Let me open the chat on this side. All right, anybody worked with fairness before? Anybody interested in this topic? I'm curious to know. By the way, while you're doing that, I've put in, I think, David, I have like 40 minutes for the talk today. Is that correct? Okay, perfect. If I go over, please stop me. I can talk about this topic forever. Um, I've put my contact information on the first slide here. So if you want to get in touch, I've put in my Twitter handle. I'll also put in my email in the chat section so you can get in touch with me or Tim if you have any questions on the toolkit or this talk. As well as I've put in a GitHub link, and this GitHub link I'll also put in the chat. This is where all the slides are, all of the workshop material is, everything lives in this GitHub. It's got an older date, but the content is pretty up to date. All right, okay, so use Power BI for data dashboards. Good, good, good. Was that in a fairness context? Let me know. All right, and in the meantime, let's get started. So the agenda today, again, like I said, we'll do a quick intro to fairness, right? It's important to define fairness and define bias before we go on with the subject. We look at some of the metrics that are useful to detect bias, and you'll see it's actually really subjective, right? Even though we are working with numbers and algorithms, this topic overall is very subjective. We look at some fairness guidelines that are provided by the AI Fairness Toolkit. And we'll look at, I'll do a quick demo and show you some Python notebooks, also give you tons of resources to go take a look at this later. So why do we care about fairness, right? This is an obvious question to ask, and I think hopefully the answer is also obvious, right? So we care about fairness because everybody wants to be treated fairly. So we know human decision, basically it's flawed in many ways. We all know that. It's based on our experiences, based on certain biases. When I think of bias personally, I think of bias as a mechanism for taking a shortcut, right? So, putting my hand on fire burns my hand, so I'm biased against the fire, right? So it's in some ways it's good. The problem is when you use bias, when you use discrimination in order to systematically put a group down or put an individual down. That's when the problem arises, obviously. So I think the idea with the whole AI and machine learning was that, hey, if we automate all of these decisions that human beings are taking with some bias, intrinsic bias, if we automate a lot of this, then hopefully maybe the bias will go away or it'll decrease. But actually what studies have shown, and maybe now it is more obvious than before, is that automating and scaling these things just compounded the bias instead of making it smaller or decreasing it. Right, so today, again, the talk, we want to ensure that automated decisions are less biased. Hopefully we can make it less biased than human decision making. All right, so how do you define fairness? There's a really good talk by Narayanan. I think he's out of Princeton. In 2018, he gave a YouTube talk on 21 mathematical definitions of bias, of fairness. And he doesn't go through formulae. He gives more of an intuitive sense of what these different metrics look like. So that's why I really like the talk. It's easy to relate to, and it's easy to understand. It's not, going through some sort of math paper. The important thing to realize here is there is no one definition that will fit all of the situations and contexts. There are many definitions based on the situation you're in. You'll look at a certain group of definitions, and I'll give you examples of that, what that might look like. Also, he mathematically proves that these definitions are in conflict with each other, and so it's really hard to remove all of these different metrics or biases at the same time. And how you define fairness and how you define bias will obviously, it also affects what metrics you will choose. For example, back in, I forget what year this was, but two leading researchers found bias when you do Google search or Google image search the word CEO. So what was happening was only 11% of the top image results for CEO showed women. At the time, women were actually 27% of US CEOs. So how do you determine what's fair? Should it be, I mean, it obviously seems like 11% seems very unfair. Should it be 27%? Because that was the reality at that time, which obviously, also has a lot of bias behind it. Or should the fair number be more like 50%? Because in population, 50% of the population is women, right? So I'm not an expert on what the correct definition should be, but at the same time, you need to have discussions like this with your stakeholders, with the project you're working on, with the domain experts, in order to come up with a definition which will then lead you to picking certain types of metrics and mitigation algorithms. So here's a case. If you are in data science, if you're working with the fairness and bias topic, you probably have heard of this algorithm called Compass. So Compass was used to predict whether prisoners in Florida are likely to commit another crime if they were given parole. So it was later investigated and found that Compass incorrectly labeled African-American defendants as very high risk, very consistently, almost twice at the rate it mislabeled white defendants. So, it obviously seems very unfair for a certain group of people. What you often don't hear is that Compass actually tried to eliminate gender and racial bias from the start. The company that developed Compass used something called predictive parity, right? So they were basing their definition of fairness on this metric, which basically says how many people, or the number of people, the proportion of people who are likely to be sent on parole was equal between the different groups. So there was a report by a company called ProPublica that found that algorithm was biased because it did not take into account balance for false positives. So there was a very high rate of false positives for African Americans versus the white defendants. So in this case, while Compass thought they were being biased based on one metric, ProPublica came along and proved that there's another metric that probably was more important than even the predictive parity metric, and that's what they should have looked at. Right now, before I go on further, I want to say like this. I'm showing you one case here, but if you go read the report, and I suggest you do, if you're interested in this topic, they have example after examples where the same thing occurs. So it's a very systematic bias against the African American group, in this case by the algorithm. I have some more examples here to show that this is how this affects our lives. So I mean, as you all know, that was one example. But if you're applying for a job, there's usually some sort of algorithm that's vetting or filtering all the applications that come in as step number 0, even before any human sees it. So here's an algorithm or a tooling that was used by Amazon that recently had to be scraped. So the problem here was the models were trained to vet applicants by observing patterns in resumes submitted over a 10-year period. And the resumes that it was trained on over the 10-year period were predominantly from men, due to the hiring decisions that were made. So the model taught itself that male candidates were more preferable, and it started penalizing applications or resumes that had things like captain of women's soccer club, or people coming from an all-women's college. It learned based on past decisions that these kind of resumes would not make for a good fit for the company. So Amazon actually tried to remove this bias, but could not due to various complexities in the system itself. So this model had to be scraped. But again, I'm hoping many of us can relate to this, right? We've all applied to jobs online, and this is a normal process that happens. This is a more recent example. This is the creator of Ruby on Rails, David, and he is complaining on Twitter about Apple Card. So when Apple Card came out, him and his wife, they both applied, and on paper, they're equally rich, they're equally wealthy, they have the same property because everything is common. But however, he got 20 times more credit limit than she did, and he decided to call Apple support and ask them what's going on. Now, when I say Apple support, it might have been the credit company that's actually giving the credit out. And they were not able to help him. Even worse, they simply said, hey, the model is a black box for us. We give it data, it comes out with some sort of credit limit, and we are not able to tell why it made the decision it did, right? So those are two sides of the same coin. So there's fairness and bias, and the other side is explainability. So when we create these models, it's very important we be able to explain how the results are being calculated. And then you can see Steve Wozniak had a similar experience on his end as well. Now, again, these are two examples. So I'm not saying the model is biased. I'm not saying it's unfair, but because of who complained, it was enough to start an investigation on Apple's end to look into the matter. But I wanted to bring it up because it's a very recent example of what's going on. A lot of times when I give this talk, people also mention, hey, you're talking about algorithms, but there are other problems in society, and given what is going on in the United States currently, I completely acknowledge that, and for this talk is very technical. I'm not an expert on those matters, so I obviously have an opinion. But what we're dealing with in this talk is completely based on numbers and sort of algorithms. So which doesn't do justice in the bigger context, but I want to acknowledge that. So today we'll look at this toolkit called AI Fairness 360. It's completely open source. What it gives you is basically a lot of different metrics. You can see 75 plus fairness metrics to detect bias. It also gives you a lot of algorithms to then mitigate those biases. And when you use what algorithm depends on where you are in your data science lifecycle. What I really like about this toolkit is that it was started in IBM research, but as I'll show you in a couple of slides, there are a lot of contributors to this framework, including a lot of people from academia, as well as other companies. Also, I like this, how their API is structured. So if you have used scikit-learn in the past, they have structured their API very similarly. So, that's a big advantage to me as well. They follow the sort of fit predict pattern or paradigm from scikit-learn. Before I show you that, I want to give you a glimpse of a couple of metrics. How do you measure bias and where does it come from? So a lot of people think, oh, bias comes from the learning that happens in the model. That might be true in a lot of cases, but I also want to point out bias a lot of times comes from your data itself, right? So this is a simple example. Students at MIT did a study of top facial recognition services. IBM was part of that, Microsoft was part of that, a lot of other companies. And they found that on average, the lighter skinned males were accurately predicted or their faces were recognized 99% of the time, whereas for dark-skinned females, it was only 65% of the times. Now, IBM, a couple of years ago, well, right now we are completely out of the facial recognition business, but a couple of years ago, they also released a new data set to try and mitigate some of these concerns and problems. So this is where you have the problem of undersampling or oversampling. Again, if you are a data scientist, these terms probably already make a lot of sense for you. So undersampling is where you have a large, large data on a certain class or a certain group, and so you then only take samples of that data to make the two classes equal. That's the bottom case here. where you have you've only taken a couple of samples from the blue class to make the data sets the overall data sets equal. The problem there is you have to be really careful. So you take a sample that represents the whole class. Versus oversampling, where instead of downsampling the bigger class, you start in some way in fashion. Maybe you start duplicating your smaller data sets in your smaller class, and based on how you do that interpolation, or if it's straight up duplicate, you might be introducing bias in your final model. So this is where your bias may be coming from your data. So people say, okay, bias is coming from data, and we know that there are certain things called protected attributes. So for example, if you're discriminating based on race, or based on age, or based on sex, why don't we just hide those attributes from our model? So the model doesn't see them, the model doesn't learn any bias from these attributes. The problem with dropping protected attributes is that there are other attributes generally in the data set that proxy these protected attributes. And so they might actually still introduce bias, even though you have removed the protected attribute. And this is a map of Brooklyn. When is this from? 1977, where banks used something called redlining, right, to discriminate potential customers by zip code. And as you can imagine, zip codes at that time, and I would say even now, certain groups of people based on their ethnicity or class or whatever you want to define, or income or whatever you want to define that as, live together in certain neighborhoods. And so what it turned out to be, they were actually discriminating against certain ethnicities based on zip code, even though they're saying we're not looking at race, we're just looking at zip code. So this is an example where removing race from the picture didn't really help much in removing the bias. It was still there. And by the way, when you read papers on unfairness and bias detection, you might still see the term redlining, and so this is what that is referring to. So there are certain terms that we need to understand before we get into the tool itself. So protected attribute, as I already mentioned, that's the attribute that is used to bias against certain groups, that divides the population into groups. So common examples are race, gender, caste, religion. Privileged protected attribute is the label of that protected attribute that results in a privilege, right? So for example, in the case of the credit card, if there is bias against women, then sex would be my protected attribute, and the privileged protected attribute would be men. When you look at fairness, you can look at it from two different angles or two different lenses. There is the concept of group fairness, where we are saying groups defined by protected attributes should receive similar outcomes or similar treatments in similar contexts, versus individual fairness, where we're saying similar individuals should receive similar outcomes. And when that doesn't happen, you have some sort of bias or unfair system. Fairness metric is the measure of unwanted bias, right? So that's how you're measuring bias, is with the fairness metric. And then favorable label, and that's easy to see what that is. So that's the label that provides an advantage to a certain group or an individual. So to start things off, like I said, the toolkit itself has 75 different metrics to detect bias. Let's look at 3 of the very common ones. So again, in practice, these 3, you may not use these 3 because they're very simple. However, they make for good benchmarks, right? So you may still want to use them. So if you see here, it's easy to understand. So what's going on here is there's an unprivileged group on top, and there's a privileged group at the bottom. And you can see this is a classification model. The results of the classification model are shown here. So you can see how many people were given positive outcomes versus negative outcomes. Statistical parity difference is simply a ratio of favorable over total. So in this case, you can see unprivileged groups, 6 out of 10 were given favorable, and the privileged 7 out of 10. And you subtract the ratios, and the metric that comes out is -10. So we can see, by this very simple metric, there might be some bias. There might be some, the unprivileged group is being treated unfairly by looking at simple ratios. Now again, what I'm saying is in reality, it's not as simple as looking at this, as we saw in the Compass case. The metrics themselves come in two different forms. There's usually a difference group of metrics, which is this, right? So the first one here. And then there's usually a counterpart of the metric, which is in the ratio format. So in this case, we're looking at the same thing. In disparate impact, we're looking at favorable outcomes for the unprivileged and the privileged, but instead of subtracting, we're taking a ratio of them. And then finally, there's another one called equal opportunity difference. And in equal opportunity difference, we are looking at the true positive rate. So as you can see now, we're getting a little bit more sophisticated. We're not simply looking at the favorable outcome between the groups. In this case, we're looking at who was given, who had more true positives in the model versus the other group on average. And in this case, again, you can see only 5 out of the 7 that were supposed to be positive, only 5 were given positive outcomes, whereas in the privileged groups, 6 out of 7 were given the positive outcomes. So, in this case, the metric itself, minus 15 versus minus 10. So again, you can see, depending on what metric you choose and how you compare your different metrics, it might, the results might seem a little bit more harsh depending on what you're choosing. And that, that may be the reality. So in the Compass case, they were looking at the false positive, if you remember. So there's another, so this one's called equal opportunity difference. There's another metric that looks at the false positive rates instead of the true positive rates. And that's what ProPublica was saying the model was not compensating for. Okay. So again, these are 3 out of 75. They have I'll show you where to go look up the definitions of all of these and how to read them. Again, I don't remember all of them off the top of my head, but they have a good guide you can use. All right, so within your group fairness, again, you can look at things in 2 different ways, and depending on what your worldview is, you may want to look at different metrics. So in the United States, we have this SAT test, which lets you get into colleges and things like that. So what they're saying here is, if the question is, do SAT scores correctly compare abilities of applicants? If you have this first view where this stands for what you see is what you get, there you're saying, yes, SAT score correlates well with future success and correctly compares the abilities of applicants. And the system is fair. If somebody's doing poorly on the test, it's because they are not well prepared, or they will not be as successful as somebody who's doing very well on the test. If that's your point of view, you may look at these 2 metrics, the average odds difference and the average absolute odds difference, and I'll show you the definitions in a couple of slides. If on the other hand, your view is that the score itself may contain some structural biases, so WAE, which is we are all equal, then you want to look at a couple of different metrics. And when I say the score may have structural biases, what they're saying is, if you're coming from a family where your parents are not, or English is not their first language, or perhaps you're coming from homes where you're coming from single parents or low income, you may not have had the same opportunity to prepare for this test as some of the other groups. So there's some intrinsic bias hidden in the score itself. And that's where you look at these metrics. So hopefully that's clear. Like, depending on how you're looking at the system and what your view is, you look at different biases or metrics, sorry. Another question is, like, where do you start off, right? How do you start detecting biases? So there are a couple of points, at least with the AI Fairness Toolkit. It gives you mitigation techniques and bias detection metrics in all of these different entry points, so to speak. So in this, again, if you're in the data science realm, this should be familiar. It's a very sort of 40,000 feet view of a life cycle of a data science project. So when you initially get your data, there are a couple of metrics that you can test your data against to see if there's any sort of bias in your metric. And that, again, could be because a class is not well represented. Maybe there's some undersampling going on and things like that. And then if you do find the metric there, then you can use some of the pre-processing algorithms. And we'll, again, look at what they are in a few slides. So that's one case. That's one step where you can sort of step in and do your metric or bias detection. The other one is while the model is being trained. So so in this case, there's obviously no detection, but there are models that are developed in the AI Fairness 360 toolkit that there are classification models that'll try to make in a way make the playing field more level for all of the different groups and classes in the data set while they're training the model. And then finally, there's also something post-processing. So once you have created the model, there are some mitigation techniques that you can use to again make the model more fair for everybody. And then what that involves is changing the labels in some way or another, right? Because you don't have access to the data. The model's already been created. And so now your only chance is to actually change the labels in certain ways to make it more fair. One thing I want to point out is as you go from left to right here, the techniques are getting more complicated and harder to understand, at least for me, right? So, and also in general, I feel like, okay, so here in the first case, okay, you're looking at the data set, it's very raw, you understand that better, and it kind of makes sense to see if there's any bias and correct that there, versus playing with the labels that the model has already generated for you seems a little bit more complex to look into and deal with. Again, the different ones, the different mitigation techniques are pre-processing, in-processing, post-processing. And the idea here is, sometimes you don't have access to the data set. You're simply given a model and you have to use it. That bias in that scenario, right? Just because you don't have access to the data set, to the training data set, you can still look at bias by just using the model. So if you have access to the data set, use the pre-processing. If you can modify the learning algorithm, or if you are creating the learning algorithm, then use the in-processing as well. And finally, if you're treating the model as a black box and you cannot modify the training data or the learning model, then you can use some of the post-processing algorithms. But that, again, that's a little bit more complicated than the other two. Now, here are the different algorithms. Again, there are a lot of mitigation techniques / algorithms that they have defined in the toolkit. So I'm not an expert in any of these, but however, what I've started doing is reading papers on each one of these, and I'll show you where to get those from. They're very interesting bedtime reads. But the one I like the one I've read recently is reveighing, and reveighing basically assigns weights to each of your features in the training example. So then you can use those weights and pass the weights into the models that accept weights as an input, and hopefully come up with a more fair algorithm. So in general, let me go one more slide over. All right, first, these are the set of papers that I was talking about. So as you can see, what the toolkit tries to do is it's implementing a lot of these papers that come out of, again, academia and other companies, and then open sources the model, right? So that's what they're doing. When you're looking at the pre-processing algorithms, generally speaking, either they are changing the weights in certain ways, that's what the reveighing algorithm is doing, or you're actually modifying the training data or input features in some sort of space. They try and do it in a way that provides transparency, and it's easier to get back to the original data, right? So the transformations are done in a way that preserves transparency. Again, you can go to the individual papers and look at exactly what they're doing. But I recommend, even if if you're not planning on doing that, just reading the docs of the toolkit gives you a little bit more idea of what's going on behind the scenes. There's also a big discussion for bias and accuracy when you're doing this sort of mitigation techniques, right? So generally speaking, if you're removing bias from your model, from your data, you will most likely lose some accuracy. And I'm using the term accuracy very loosely here. You know, that could mean different things based on what models you're looking at and what metrics you're looking at to evaluate your models. But generally speaking, this is true. So, you know, there's a trade-off here. And how do you decide how much accuracy you want, right? So as data scientists, you know, and especially in Kaggle competitions, everybody wants to get to the most accurate model. I hope to start like testing for bias and those kind of things in those competitions as well, because it's so relevant. But at the same time, you know, how do you decide? So there's a couple of things here. One is, you know, what is your model trying to achieve? So how much impact will that have on people's life? Again, that's very subjective. It's hard to come up with a single number that'll define the rest of my life, right? So you have to really get together with the different stakeholders that are impacted by your model, by your algorithm, and then come up with these numbers. There's also legal issues. So, you know, what you're doing, or if your model has a bias based on something like race or sex or something like that, or age, that's actually illegal in the United States, and I'm sure a lot of countries around the world. So there's some legal implications. There are always ethical implications, right? So and trust, ethics and trust. So a lot of times with these algorithms, you know, even with the Apple episode that happened, you'll lose trust with your clients and with your customers. So again, you know, the bias versus accuracy debate, for me, it's you know, it's sort of clear. Well, actually, sorry, it's complicated, because based on the scenario you're in, you always want to be, you know, you remove bias, obviously, but also accuracy is important. Otherwise, you know, why are you getting paid to create these models if you're saying, hey, flip a coin and you'll get the same results? So, all right, so hopefully, you know, you have a good idea of what bias is. I would say preventing bias is hard. Again, because everything is so vague. Everything is depending on the context you're in. Here are a couple of tips, right? So work with your stakeholders early to define fairness. How you define fairness, how you define your protected attributes will result in you picking different mitigation algorithms and picking different metrics to detect bias. The next tip is apply the earliest mitigation technique. If you can work with your data, look for bias there, apply your mitigation techniques there. It's easier to understand, it's easier to explain to people what you're doing. Number 3 is check for bias as often as possible, even after you deployed your model in production. It's, you know, bias can creep in after the fact as well, based on the data that's coming in. And so this should be part of your, as you're testing for your, you know, for your evaluating your model over time to see if the performance goes down or not. Just like that, check for biases over time and see if biases creep in over time. The last one, you know, I'm going to show you AI Fairness 360, but it's meant to be used in certain settings, and they have defined that very well in the documentation. So if you do use this toolkit, this is the caveat. All right, so let me show you a quick demo. Excuse me. I'm going to end my slideshow and go here. 1 second. Oops. What am I trying to do? All right, so do you see the GitHub page, David? Okay, perfect. Thank you. So I've got the slides here. Feel free to check them out. I've got a bunch of links here, including all the papers that were listed in the presentation, as well as the other links I'm providing, right? So ProPublica article. There's a talk, very good talk on the facial recognition stuff I talked about from MIT. But let me go ahead and show you. So AI, sorry, Fairness 360. Sorry, I'm going about this in a roundabout way because I didn't have this link, but this is the link for, let me put this in chat. All right, so this is the link for the project homepage, plus there's a really nice demo here. Before I get into that, you can see they define all of the different mitigation, or sorry, all of the different metrics here. And it's really cool. If you click on any one of these, it'll take you to the source code. So you can go and, you know, there's the paper or the reference on the, you know, where this model or this mitigation metric came from. So you can go read that, but also you can, if you're interested in, I know some people like to read source code to get a better understanding of how this was implemented. So again, all of this is open source and very transparent. You can go look at any of these metrics, or at any of, these are algorithms, sorry, and the metrics are down here. So you can look at either of those two and see how they were implemented. Let's try a quick demo. Okay, so they have created this web demo, but behind the scenes, they're using the AI Fairness 360 toolkit. So they have 3 different use cases here. One is the Compass one, which we talked about. The other one is German credit score, and that's basically you know, deciding whether to give a loan out to a person or not based on a number of different features about them, about the person. And the last one we look at today is the adult census income. So if I click on this Learn More, it opens this page. So this is the UCI repository, and this is where the data is coming from. And the class, the task here is to develop a classification algorithm that will tell me if somebody will make over 50,000 or less than 50,000 based on these different factors, right? So based on how old they are, based on where they're working, if they're working, based on their education, and then, you know, the stuff that we want to be careful about, given their race, given their sex, those sort of things, and of course age, right? So let's pick that as our demo for today, and then somewhere there's a next button. Okay, next. All right, so I've picked my data, and what it's doing now is actually detecting bias in my data itself, using the different metrics that we talked about before. Remember, we talked about statistical parity. In this case, it's saying the number of favorable outcomes. In this case, the favorable outcome is more than 50,000. It's picked the, by the way, when you're using this toolkit, as with others, you have to tell the framework what your protected attribute is. So in this case, it's race, and you have to tell it what you think the privileged groups are and the unprivileged group is. So in this case, white as race is the privileged group, and non-white is the unprivileged group. So this is saying, just by using some classification algorithm, it doesn't tell me what it is. It's saying the accuracy is 83%, but there is some bias. So 2 out of 5 metrics are showing bias. The statistical parity difference, that's the favorable outcomes between the privileged and unprivileged classes, coming out as minus 18%. And of course, the disparate impact, if you remember, that's just a ratio of the same metric. And so that's coming out at 0.55. When we look at sex, it's a little bit worse. I'm trying to get rid of the zoom thing. Okay, when you get to here, you can see in the protected attribute is sex, privileged is male, unprivileged is female. In this case, more metrics are showing bias. So good, so I have an idea of there is some bias in the system. Let's go ahead and try some mitigation techniques. Again, this is a built demo. It's just a website on top of AI Fairness 360. It doesn't show the actual source code, although I'm sure this is open source as well. But when I show you the notebooks, you'll see the source code as well. So we talked about reweighing. Let's look at reweighing. So this is a pre-processing technique or mitigation algorithm. It works on the data itself. And if I click on next, now it's going ahead and applying the different techniques. Or sorry, it's applying reweighing to our data set itself. And as you can see, it's able to reduce by using different weights for our 2 classes. It's able to reduce my the bias metric of statistical parity difference went from minus 0.18 to 0.1, and then also the disparate impact. Now, if it's a disparate impact kind of metric where it's a ratio, you want it to be as close to 1 as possible. For a subtraction, you want it to be as close as 0 as possible. So this one went from 0.5 to 0.74. Again, an improvement. However, you can see here the accuracy, which is the criteria to evaluate this model, has gone down from 83% to 82%. Now, can I live with that? Can we live with that? You know, you have to, again, have this discussion with your stakeholders. But in this case, it seems like this much difference or this much improvement in my bias with 1% decrease in accuracy might be okay, right? So again, you have to study these things and have a discussion around it. Again, with the protected attribute being sex, again, it's gone down by quite a bit. Now I know I'm running out of time, so I'll show you one last thing. Again, like I said, this is a demo prepared by the team. But as data scientists and developers, if you want to look at the source code, you can go to resources and then tutorials. And there are a lot of notebooks in the AI Fairness 360 examples GitHub page. And again, I'll put this in chat. Where did my chat go? All right, I cannot seem to get to chat. Oh, here it is. Sorry. Okay, I see there are a lot of questions on the Coursera stuff that Tim is answering, so good. All right, so here's the different notebooks. And if we just looked at, if you remember, the adult income one and the reweighing algorithm. So let's look at how that looks in code, right, instead of clicking buttons around. So if you're familiar with Jupyter notebooks, these things are called, if you're not familiar, these things are called cells, and then you start writing code and running these cells one at a time. So the first thing we're doing is importing all of the different libraries we need. You can see it's importing something called binary label data set. So this, we are telling it that we're interested in the metrics for the binary classification. So in this case, if you remember, the less than 50,000, more than 50,000. And then we are importing our data sets. We are importing our metric for binary label. And then we are importing reweighing as our mitigation algorithm. And then we go down here. This is just, if you want to work with a different data set, you just change this flag. In this case, we are working with the adult data set. Now, this is important. This is where I was saying you tell it, let's see. Right, so in this case, the data set original train features. Yeah, so in this case, we have already told it what the favorable label is, what the unfavorable label is, just because we are importing the right class. So in this case, when we are importing this adult data set, this class itself, it's got certain attributes for favorable, unfavorable, protected attribute, and all of that. If you're importing your own data set, you would have to subclass one of the base classes and then define those things for the framework to understand. And then basically, so in this case, you can see, we have told it what the attribute is sex, the privileged, and the unprivileged is 0. So the 0 being women, the 1 being male. And then if I go down here, here's where here is where I tell it to give me the metric, the binary label dataset metric. I tell it what my data is. I tell it what my unprivileged groups are, privileged groups are, and it comes back with minus 0.19. And this is what we are looking at on the web demo as well. Then I tell it, okay, use the reweighing technique on my data set, and then I do another. I ask it again for the data set metric on my reweighed data set. And in this case, it's telling me it's completely removed the metric. This, as you probably know, this generally doesn't happen in real world, but in this case, the data is in such a, the data or the technique was, I guess the mitigation technique in this case gave me a 0, but generally doesn't happen. It's a sample, it's an example. And then we look at, they use the classification algorithm on the original data, and they use it on the reweighed data. And then there are some graphs at the bottom. Again, I'm running out of time, but if you can see here, they're comparing the accuracy with not the disparate impact, but 1 minus disparate impact. And that's just to create the graphs in a way that it's easier to understand. And then this dotted line is where my classification threshold, right? So now based on, as you can see here, my accuracy, as my accuracy goes up, so does the bias goes up as well. And so now I have to pick a point here where I can maximize my accuracy while minimizing my bias. This is before reweighing was applied, and this is after reweighing was applied. So you can see here that, well, here as well, as my accuracy is going up, my bias in some ways is going up as well. But overall, reduce my bias by a lot. But the two graphs, by the way, are looking at different things. This is looking at the disparate impact. This is looking at the average odds difference, which is a different metric. But yeah, so the notebook kind of goes through on how to do this using reveighing. If I go back to the GitHub page, there are others as well. So there are pre-processing algorithms, and also there's in processing and in post-processing examples of notebooks with the different data sets that are shown here. So take a look at that. There's another one that uses Lime, if I can see. Yeah, so this is using Lime, which is another explainability framework. And they're trying to show, the notebook shows how if you use, you know, the explainability and AI fairness together. Now we do have another framework for explainability as well, just like for fairness. I'll put that link in the chat as well. But with that being said, let me go back to my slides. I think I'm done at this point. So we looked at the demo. I showed you some examples. If I were to give you one more resource, so one is the GitHub page, which has everything. The other resource would be the Slack channel. And this is where the developers and the contributors to the framework, not just IBMers, but all the contributors chat about things like fairness and bias. So, you know, there are way smarter people here than I am. So if you have questions, you know, ask us, or also go to the Slack channel, join the Slack channel, and they're very friendly. You can ask questions there as well. With that, Tim, I'm going to hand it over to you. See if you have anything to add.
Yeah, I just wanted to point you to something that was brought up in the chat by Gary. Is it about the recent example in the UK where they try to predict people's university scores in lieu of tests, and it turned out to be horribly biased. Had you heard about that?
I had not, but I'm going to look that up.
I put a link in there. They got a bunch of news coverage. I just put in one of the links. But yeah, it looks like they came up with an algorithm that did not take into account any of the stuff you talked about today.
Yeah, it's, you know, it's interesting. We don't like, this is not taught anywhere, right? Now I see courses on explainability and bias come up in universities and Coursera, but in general, this is not a subject that's talked about to students. And so I can see why this is not of concern unless something bad happens, and then you go back and try and put out the fires.
Yeah, that's apparently what happened here. They had a result that ticked a lot of people off.
Yeah,
and then
exactly.
they kind of walked it back. But yeah, so thanks for sharing that, Gary. That was a great example, a recent example of bias in an algorithm.
Yeah, if I had one ask for everybody in this group, would be, next time when you attend a data science conference, a data science meetup, even if it's on, you know, something completely random, bring up the topic of bias in your questions. Like, you know, you don't have to be mean to the speaker, but you can always, you know, you can ask the audience, do a polling. Hey, have you heard, you know, do you look at biases? If not, why not? And you should, and point them to something like this, or, you know, there are other frameworks as well. But I think it's our duty as developers and data scientists to make everybody aware of this. And I'm glad that's happening. All right, David, I'll pass it back to you.
All right, thank you. Thanks, Upkar. That was a very insightful talk. And I think it's really important for us all to, especially in this time and age, for us to be aware of biases in our models. So I think now it's open for, the floor is open for Q&A. Because we do, actually before that, just a quick update. I got a message from the next speaker, Wat, that she is having trouble with her Wi-Fi and she probably can't join us today. So we'll probably have to end the session after the Q&A. Yes, so so actually to kick off the Q&A, I do have a question about the protected attributes. Because in order for the metrics and for the algorithms to work, first we have to define the right attributes that we want to measure. And do you have any guide on how we can be more aware of these different attributes aside from the obvious ones? For instance, you mentioned about the zip code being one of those that could be correlated with the other protected attributes. How would you kind of suggest that we go on and explore the possible attributes we should be more sensitive towards?
Yeah, that's a great question. And I wish I had like a magic bullet to say, hey, try this and magically your proxy attributes will bubble up. Unfortunately, they're, from what I've read in the research, it's really hard to do. One, something that they share or they ask to do is work with the stakeholders and work with people who are living in the system and who are actually part of that system. And they know a lot. They have a lot of sort of intuition and knowledge that is hard to discover through models and through metrics, right? So that would be my number one suggestion would be, if you're working with test data, go talk to universities, go talk to people who design the tests, and based on how they think, based on your discussions with them, I'm sure some of these proxy attributes will come up, right? Mm-hmm. That's one. Somebody suggested, hey, treat every attribute as a protected attribute because you can do it one at a time. So why don't you take all the groupings and permutations of the different attributes and run the AI Fairness 360 and see if a bias, if a very obvious bias comes up with certain attributes, and maybe that'll give you a hint. Maybe that bias, even though it's not as, if it's not the normal protected attributes like sex and age, maybe if there is bias in there based on the metrics from AI Fairness 360, that could be a starting point, maybe. I think the first idea to me seems more doable and more I think so. When I worked in consulting, it was the same thing. Like, you have an idea that the system, but people who have been in it for 30 years, 40 years, the kind of knowledge and intuition and the hidden, like the hidden gems and whatnot that they understand and know, it's kind of hard to use just science and maths to figure that out. So yeah, that would be my number one tip would be, talk to the stakeholders, talk to somebody who's very knowledgeable about the domain. It's a good question though.
Yeah, thank you. Do you have any questions from anyone in the audience?
Another question I get, so I'll pitch in here. Another question I get is, what we have looked at so far is structured data. Like, so can AI fairness deal with unstructured data, right? So right now, structured data is sort of what they look at. It's the primary form of data that's studied in not just AI Fairness 360, but in literature in general. So the unstructured stuff is starting to get more attention from the fairness community. But for now, it's more or less focused on the sort of the database-y kind of structured data. So yeah, if anybody was thinking about that or had that question.
Got a question just out of curiosity. Has anyone tried to use machine learning to then to kind of elucidate the biases that exist in our systems? Because with machine learning or the existing models, they seem to really bring to light the biases that exist in our systems. And have they been used in the other way, which is since actually these models are telling us that there are these biases, and we can use the output of these models then to tackle these biases in our society or in the companies, etc.
Yeah, see if anybody else has any experience with that.
Mm-hmm.
To me, it's like a lot of times we know somewhere deep inside there is some bias happening, just based on our experiences, based on how we live as human beings, and there's obviously a lot of bias in our history and happening right now, and we're creating more and more as well. So a lot of times for me, like these numbers kind of put science or math behind it, right? So, because some people don't believe that there is such a thing happening, right? People live in their worlds, and unless you're affected by it, unless somebody you know or you yourself are affected by a certain bias, it's kind of hard to put yourself in other people's shoes. And so for me, like a lot of these techniques and the math behind this is important to back that up. But it's hard. It's hard because it's so vague, and it's depending on who you talk to, they'll come up with a different definition of fairness. They'll come up with a different definition of bias, and a lot of it is like, am I or my group of people to be gained by this decision, or it's very personal, David.
Yeah,
that's why it's kind of hard to.
I understand. Yeah.
I see a question though. Can you give more detail on the interface platform software required to run GitHub code? Example, Jupyter Notebook, Visual Studio. Oh, that's a good question, Gary. Thank you. So the fairness toolkit itself is, let me share my screen real quick again. My God, they decided to dig a hole or something near like outside my window today. So I'm going to steal your screen share for a second there.
Yep, go for it.
Oh, that's interesting. Okay. All right, so this is again back to my GitHub page. Somewhere, did I put my workshop here? I did not put my workshop here. So I'm going to give you a link for the workshop itself. But basically, it's just a pip install, the AI Fairness 360. That's one way to get it. So right here. So if you're running in a Jupyter Notebook, let me go to, yeah, basically it's this, pip install AI 360. Now, there are some requirements or prereqs to installing this, and that's what I was looking for in my workshop. Tim, I'll send that to you after, and David, if you can share that with the audience. We have created a really nice PDF on what you need if you were to do this locally using Python or using Conda. So there's just 2 or 3 different prerequisites that you need when you're installing AI Fairness 360. And then Gary, basically after that, it's up to you, right? So you can use whatever editor you like. You can use VS Code, you can use PyCharm, you can use something like Watson Studio, which is IBM's product. To write Jupyter Notebooks, you can reuse Jupyter Lab. You just need a Python environment. That's all you need at this point to start using this, because it's simply a pip package. Does that answer your question, Gary? And we'll share, so we have made a, how to run it locally on your system on Python/Conda, and we'll make sure we share that with you so you have the steps needed. All right.
All right. Does anyone have any last burning question?
If you think of questions later, again, I'll put in my Twitter handle down here. Please do get in touch. And also, my site had the Slack channel, so also join there. Even if you're not working on this right now, the kind of discussions they have there is it's very meaningful, and I get to learn a lot just by being there and listening to the researchers and the academia talk. All right, thank you very much, David.
Thank you. Thanks, Upkar. Well, yeah, thanks again to the great talk, Upkar. And also thank you again to IBM for sponsoring today's meetup. Sorry again that we couldn't, the second speaker couldn't make it today, but probably we'll try to squeeze her in for the next session. Otherwise, thank you all for joining today's meetup as well. Hope to see you at the next one. Thank you.